my advisor, Doan Choi. Let's get started. First, I will briefly introduce vision transformer. As you know, in vision transformer, input image is split into multiple patches, and these patches are passed through a linear projection and converted into tokens. And these tokens are also passed through a transformer encoder, which is composed of multiple attention and MLP layers. Through this process, we can get a strong performance with ViT, but there is some problems. One major issue is that ViT has a massive model size, which leads to prolonged training time and slow inference speed. Therefore, reducing the computational cost of ViT has gained attention these days. There are several techniques to reduce the computational cost of ViT, one of which is reducing the number of input tokens during inference time, also known as token compression. In the field of token compression, token pruning was the first technique. Token pruning is a method that identifies and prunes unimportant tokens with respect to some heuristic criteria, such as attention score of the class token. However, there is a problem. The information loss occurs caused by pruning the tokens. To address this issue, token merging technique is introduced. Token merging is a method that merges similar token pairs rather than just completely discarding less important tokens. Specifically, in TOMI, a baseline token merging method, they first divide the tokens into two groups and then identify the most similar token pairs to merge. Through this process, we can reduce the information loss caused by token pruning. However, in my point of view, there is a remaining issue that needs to be addressed. We observed the limitations of existing static token merging method is that they reduce the same number of tokens regardless of the image characteristics. However, among the images, there may be samples that are easy to merge and the others that are hard to merge. As you can see in this figure, we can intuitively think that for each sample we can merge more aggressively, especially for this blue sky background. However, for hot sample we should preserve more token since it contains diverse and complex information in this case. So we guess that a threshold-based merging approach is more appropriate than static top-down merging. This is because threshold-based merging allows us to merge token pairs adaptively based on image characteristics. As you can see in this figure, in static top-down merging, the number of remaining tokens is 65 in this case. So the number of remaining tokens is the same. However, when we apply the threshold-based merging approach, the number of remaining tokens vary across images. So we decided to use a threshold-based merging approach in our method. This slide shows the overall process where we merge the tokens across layers. And this process is composed of 4 stages: grouping and matching, thresholding, batch computation, and merging. First, in grouping and matching stage, we first divide the tokens into 2 groups and find the most similar token pairs. And in the thresholding stage, we identify the token pairs whose similarity scores are higher than predefined threshold. At this point, an important question arises. Question 1 is about how to enable batch processing. In a threshold-based merging approach, due to its adaptive nature, batch inference is not possible. This means that within a batch, the number of remaining tokens vary for each image. To address this issue, we proposed batch adaptive merging, in which the number of mergeable token pairs after thresholding is divided by the batch size to get the actual number of tokens reduced per batch and layer. So using this technique, we enable batch processing in a threshold-based approach. The next question is about how to effectively adjust threshold. In a threshold-based merging approach, we can either set a constant threshold or set a different threshold for each layer. So how should we set the threshold for each layer? To explore this, we measure the layer-wise impact on information loss during merging. In this figure, the x-axis represents layers and y-axis represents estimated information loss. And in this figure, each line represents the information loss that occurred when tokens are merged based on a given similarity, and each bar is the mean of these lines. So as you can see in this figure, we could find that the different losses occur across layers even when merging is performed with the same similarity. So based on this analysis, we thought that we should apply a higher threshold in initial layers and gradually decrease the threshold to further reduce the information loss. Through this analysis, we proposed a layer-dependent thresholding strategy in which we set higher threshold in initial layers and gradually decrease the threshold while approaching final layers. And this formula represents what I just explained, and the right figure shows how the layer-wise threshold vary across layer. So, next question is about how to initially group tokens. This means that when we perform merging, we should first divide the tokens into two groups. So how should we? What is the best strategy for grouping tokens? For this, we consider merging size, which means the number of tokens included in a specific token due to merging. So in this formula, Xij is the merged token of Xi and Xj, and here Ni and Nj is the merging size of Xi and Xj. So to summarize, Xij is the weighted average of Xi and Xj, and in this figure, we designed the amount of merging error with this orange area. So as you can see in the initial layers, when we perform merging with small merging size, the amount of merging error remains low. However, in the final layers, when we merge the tokens with large merging size, the merging error significantly increases. Since the merging size tends to increase in deeper layers due to its hacked architecture with ViT, we thought that another grouping strategy needs to be applied in deeper layers in order to reduce the merging error. So, based on our analysis, in initial layers we divide the tokens into two groups using alternate matching. However, in contrast, in the final layers, we first sort the tokens by their merging size, then divide the tokens into two groups. We called this process size distinctive matching, so using this technique, we can further reduce the merging error. So this slide shows the final version of our method. So to summarize, in the initial layers, we first divide the tokens into two groups using alternate matching. Then we count the number of tokens whose similarity scores are higher than our layer-dependent threshold. Then divide that sum by the batch size to get the actual number of tokens to reduce. So using this actual number, we perform merging. And in the final layers, instead of dividing the tokens into two groups using alternate matching, we first sort the tokens by their merging size, then divide the tokens. After that, we just follow the merging process usually in initial layers. Next, I'd like to share our experimental result. In our experiment, we compared our method with existing token compression method like ViT, 2Me, and MCTF. And in this figure, the x-axis represents zip loss and y-axis represents one accuracy. So in this graph, if a method is located in the top left corner of the graph, it indicates that it achieves the best performance among all the compared methods. So as you can see in this figure, our method ATM is located in the top left corner of the graph. It indicates the best performance on them. And this slide shows the visualization results. In this figure, original refers to the input image and to me refers to the baseline static top arm merging method, and ATM is our method. As you can see, to me merged the same number of tokens regardless of the input image. The number below each image represents the number of remaining tokens after merging. However, our ATM method, in our ATM method, for each sample we merge the tokens more aggressively, while for hot sample we preserve more tokens to ensure safer merging. To summarize, ATM adaptively controls the level of merging quantity based on the complexity of images. Let me summarize the contributions and discuss our future work. We proposed ATM. ATM is a method. ATM is a novel token reduction method that minimizes redundancy without fine-tuning. And in our ATM, we proposed threshold-based adaptive merging, attractive merging, and size-distinctive token matching strategy. As for future work, ATM could be extended to diverse architectures such as LLMs or Mamba-based architecture for adaptive compression. And it would be interesting to combine ATM with PFT like LoRa, ViT, or adapter-based fine-tuning. That's the end of our presentation. If you're interested in our work, please visit our website. Thank you for listening.